Hi class, we're on chapter 19.3. This is entropy and the second law of thermodynamics. So the second law of thermodynamics states about spontaneous processes which results in an overall increase in entropy of the universe. The way I like to describe this and the way I thought about it when I was a student is you can clean your room, but your room will always get dirty. And unless you are one of those people who always put things right back right after you use them, your room will always be dirty. And I used to say, well, that's entropy. That's just the way things have to go. So there will always be an overall entropy, which is a degree of disorder or randomness. So it's disorder, or you can think of it as a way of spreading out a system's energy. So the more the particles can disperse out into the surroundings, the more entropy there is. So disorder. The opposite of entropy would be something very organized, patterned, concentrated. This wants to be the exact opposite, just disorder spread out. Entropy is a state function, so that means we don't care about how it got from point A to point B, it just got there. So two people can take two different trails, but they both start at the same spot and they both end up at the same spot. But one trail was a lot longer than the other. We don't care about that. Okay, so factors affecting entropy. And the easiest way to remember entropy is it's disorder, but an easier way for me to understand this is thinking of spread out. This right here. Another way is to describe how it spread out a system's energy. So if you're asking if you're dealing with something with energy, this entropy, ask if it's being spread out. And that should give you an idea of what you're dealing with. Excuse me. So state of matter, when we're dealing with solids, liquids, and gas particles, gas have the most entropy because they're not organized. There's random patterns to them, and they will spread out as much as possible. So the entropy there is large. Solids are very highly organized, so that's going to be low. The entropy there is low. And then liquids are less than gas particles. However, they have more entropy than solids. So gas particles have the highest entropy than liquids, than solids, and solids do have vibration to them when they get excited, so they can move. It's just they cannot move out of that place unless they have enough energy to break those bonds. Temperature, an increase in temperature also increases kinetic energy, which gives whatever it is that we're looking at more energy to move, whether it's through vibration or actually movement, which can allow greater entropy. Gases is an increase in kinetic energy motion, and motion of gases allows the energy to be more randomly dispersed. So the more energy gas particles have, the more they will move, the more random they can have patterns, and the more they can spread out. And also another way of a factor affecting entropy is increasing the number of particles. The more particles that can disperse, the greater the area that will be covered with entropy, with an increase in entropy. So entropy is positive if there is disorder, if they are spread out. If it's negative, then that means that entropy is not going to occur. So if it's positive, it's an increase in entropy. So a phase change from a solid to a liquid because it's spreading out. A solid is very organized, it's stuck in it where it's at. Yes, it can vibrate, but it cannot move out of that spot, but a liquid can. So liquid has more disorder than a solid, so there's an increase in entropy. A phase change from a solid or liquid to a gas. Gas is the highest entropy, so if it can go from a phase change from a solid to a gas or liquid to a gas. The dissolution of a solid in aqueous solution, this is very easy. Think of sodium chloride like a salt crystal. That's a crystalline structure that has a very organized pattern to it. But when it dissolves in aqueous solution, it's just ions and they are spread out. So this allows an increase in entropy. Increase in temperature within a phase, or an increase of number of gas molecules. So melting ice is an endothermic process, yet it does occur spontaneously above 0 degrees Celsius. So when a solid melts, the particles have more freedom of movement. So even though it does need energy in, this will occur because it will go from more of an organized, even though liquid is less organized than solid, it's still more of an organized pattern. You can see in this, look at these pictures. But once, when it goes from a solid, which is very organized in pattern, to a very disorganized, somewhat disordered, not really a pattern to it. So it is increasing and spreading out. So that's where the entropy can occur. So more freedom of motion increases the randomness of the system. When systems become more random, energy is released, and we call this energy entropy. So there's an increase in entropy. Water evaporation. Water will go from somewhat disordered. However, it will go into a gas, and the gas is highly disordered. So it's going to increase in entropy. So this will occur, resulting in a positive S. Salt dissolving in water, you can see here as a salt crystal. It's very ordered pattern. However, when it is in solution, it dissolves into ions and it's very disordered, no pattern to it. So the entropy will increase. So here you can see with phase changes. If we go from solid to liquid to gas, the entropy will increase. It will be positive. But if we go from gas, liquid to solid, it will decrease because it's becoming more concentrated. And we don't want that. The opposite of spreading out is the concentrated. We don't want that. So this is a decrease in entropy. Entropy will not occur. So let's look at some examples. So here we have a reactant that's a solid, and it produces a solid and a gas. So in this case, does this qualify for an increase in entropy? And the answer is yes. Yes, this goes from a solid to a solid. There's no change, but it also produces a gas, and the gas will spread out into the system, into the surroundings. And because of that, it will increase in entropy. So if we look here, it will be a positive S. Now we go from a gas to a solid, and that is decreasing the entropy. So it's becoming more concentrated, more pattern. So that's a negative. So the entropy will not occur here. There will not be an increase. See, it's going from very orderly and organized to very spread out in disorder. So that is a plus. It goes from a solid to a gas. And condensation appearing on a bathroom mirror is a gas becomes a liquid, which is becoming more concentrated. So that is a decrease in entropy, which is negative. So the second law demands that entropy of the universe increases for a spontaneous process. Yet, processes like water vapor condensing are spontaneous, even though the water vapor is more random than the liquid water. It's a process is spontaneous, but the entropy change of the process is unfavorable. There must be a large increase in the entropy of the surroundings. So what this is saying is that entropy wants disorder, not order. But yet some of these reactions still occur, even though it's not showing based on what we're looking at that it should occur. So something else is happening. And what's happening is that entropy is releasing heat into the surroundings from the system. And that heat is being dispersed out, and it is causing entropy. So that is allowing this to work. It's causing disorder into the surroundings from the system. So that heat is causing disorder. It will occur even though the actual reaction is causing more order. So some of these conditions will all outweigh some of the other ones, and it can still occur. So if you remember, if it's a universe, we have a system where the reaction's taking place. The surroundings are exactly what it is, surrounded around it. These two together become the universe. So spontaneous processes occur because they release energy from the system. Most spontaneous processes proceed from a system of higher potential energy to a system of lower potential energy. Remember, when we look at graphs, sometimes the reactants have higher energy, and once the reaction has occurred, it's lower energy, which means that heat has to be released. That's exothermic. But there actually are some spontaneous processes that proceed with an endothermic reaction, and that is a system from lower potential energy that results in a higher potential energy. But that is, so endothermic reactions still can occur, and they still can occur spontaneously with entropy. Okay, so entropy and probability. Entropy increases when there are more energetically equivalent ways to arrange the components of the system. So how would we detect that? Well, we can use this mathematical equation by Boltzmann. It's what S stands for entropy. Let's go to the next page. K is the Boltzmann constant, and we have it here. W is the number of energetically equivalent ways a system can exist. It's unitless. And again, entropy is a state function. So this is S is equal to K, the natural log of W. And we're going to cover that more in a while, so it'll make sense to you. Okay, so K is the Boltzmann constant derived from the gas law constant R in Avogadro's number. So R is the gas constant, and Na is Avogadro's number. W is the number of energetically equivalent arrangements called microstates that are possible for the system. So this has to do with, if you think about it, if you've taken statistics, it has to do with probability. So if you toss a coin, you can look at the number of outcomes of that coin and how many times you toss it, which way does it land. This is very similar to that. How many probabilities do you have? So what if I add more coins? Then you increase the probabilities of one landing on one more than the other side. And that's what we're going to look at. That's what we call microstates. And from the microstates, we have a macro state, which is macro, which is bigger. So that's the state defined by a given set of conditions. The most likely microstate is the one with the most possible microstates. And I'm going to, I accidentally typed this wrong. The most likely macro state. This should be macro state, not microstate. So we're going to look at microstates, and then we're going to pick the one that's most likely fits this description of the one with the most possible microstates is the most likely macrostate, the one that's most likely to occur. So each possible arrangement of particles represents a microstate of the system. It's the equivalent microstates comprise a macrostate. So I have examples to make sense of this. And I don't like the example your book gave, so I have other slides. The most likely macrostate is the one with the most microstates. That means the most possible outcomes. A system will spontaneously move to a more spread out arrangement, which is why I'm putting that there so you can understand what we're going to look at. And the tendency towards disorder is statistically a probability. So this is what your book gave you. It describes two different systems. System A only has, think of it as one floor. System B has two floors. So it can spread out more. So this would be, you have first microstate and second microstate because you can flip these. And those are the probabilities. So in this case, this has two microstates. So this would be the macro state. This is the most with the more probability. So this is most likely the macro state that would occur. However, if that definition doesn't work for you, I pulled some slides from another book that I taught elsewhere. So if we look at this box, there's a divider that's pink. And in this box, all the gas particles are on one side. They can't go anywhere. So the only possibility or probability is that one side, that all those molecules there, that's it. They're not going anywhere. But what if I pull that divider up? Now they will spread out. They will spread out more because entropy states it wants to spread out. That if it can occur to spread out and cause disorder, it will. So that will, the minute you open it, those particles are going to disperse spontaneously. That's entropy. Scientists can use probability to explain this phenomena and derive mathematical relationships. So I'm going to show you these probabilities. So we look at a box. Now this box has a divider in between it. And we kind of put dots. So it looks like there's 4 squares here, even though these can go back and forth and this can go back and forth, but they can't go across. So if we have one particle, there's only 2 possible arrangements, up here or down here, because this is a divider. It can't move. So that W, and remember that W, if we go back, is the number of possible microstates of the system. So in this case, there's only 2 arrangements. It's either at the top or the bottom. It's not doing anything else. But what if we add more boxes? So, and another particle. So the first thing it is will be AB. It could be BA. It could be AB at the top, and it could be AB at the bottom. So now we have 4 possible arrangements here, and W equals 4. Okay, but what if we remove the divider? If we remove the divider, that means that we can have so many more possibilities. In fact, 16 total, besides including the ones that we just looked at. So if we look again, we have these 4, and as you can see, they're on one side. But what if we do the mirror image where we do this exact same patterns on the other side? That's another 4. So this W would be 8. So if you guys mean it's AB, BA, AB, AB. So if we use the divider where they can't touch this left side but are only on the right side in the same exact pattern, that's W would be 8. But once we remove that divider where they can go throughout, so this is the one that we looked at. This is the mirror image, these 4, so this is 8. But if you look at these are now all spread out. We have AB, BA, AB, BA, crisscross is AB, BA, AB, BA. So this makes more, we have more macrostates here. So this would be the probability of what could occur. So how do we understand W? Well, W is, excuse me, so we use the X. X is the number of locations, and N is the number of particles. So for the first one, if we looked at it, we looked at here, and it had 2 locations, but only 1 particle. So that's where the 2 with the 1. But what if it had 2 locations and 2 particles? So if we look at this one here, it had 2 locations and 2 particles. That's where the 2 to the 2nd power. Then we had 4 locations, and we have 2 particles, and that gave us 16. So this is where this W is coming from. And your book doesn't do a good job in this section stating that. Okay, so here we have a macro state here with these 4. Out of the 16, we have another macro state here. And then we have 8 macro states. So this is the one that's most likely to occur because it has the most probabilities. All right, so let's look at this. Predict the sign of delta S for the following change between macro states. So particles are on both sides, and then all of a sudden they're on the left. So this would be a decrease in entropy because it's become more concentrated, and entropy is the complete opposite of that. So it's negative, but then you might also want to know how many macro states. So we have 4 different locations it can go, and 2 particles. So there's actually 16 possible probabilities of what could occur here. Okay, so consider these changes in the possible distributions of 6 gaseous particles. Basically, which one has a positive delta S, which means which one has an increase in entropy. And in this case, we can see here this has 3. It only has 2, so this became more concentrated. That's not it. We have 3, which would be ideal for entropy, and it went to 1, so this became more concentrated. That's not it. And then we have 2, and it became 3. So A would be the one because it's spread out, and it has an increase in entropy. So that would be positive. All right, so here's review. Thermodynamics deals with predicting conditions necessary for a process to occur, which is not possible considering enthalpy changes alone. So some enthalpy plays a part, but we also are now looking at entropy. The second law of thermodynamics states that all spontaneous processes result in an increase in entropy of the universe, where entropy is the degree of disorder randomness. So this explains very well why somebody's room gets dirty and will stay dirty no matter how many times you clean it. It will just always go to increase of entropy. Can't help it, just the way it is. Equivalent microstates form a macro state, and the most probable, the one with the highest number of microstates, is the macro state. Positive changes in entropy accompany phase changes. So when you go from solid to liquid to gas, ask yourself, if it's spreading out more, then there's an increase of entropy. Is it becoming more concentrated? It does not. Increases in temp within a phase and processes that result in an increase in the total number of moles. And then we have Boltzmann mathematical definition of entropy. So we have S equals K, which is the Boltzmann constant, and the natural log of W. And W is the energetically equivalent arrangement, the microstates that we're looking at. That's it.